Then the other things that we discuss under differential analysis of fluid flow is conservation of linear momentum, which we will study through Cauchy's equation. We derive it by using the divergence theorem, just as we derived continuity equation using diversion theorem. Derivation using infinitesimal control volume, alternative form of Cauchy's equation. So you can see the similarity. We are doing the same things that we did while deriving continuity equation. Then deriving it using Newton's second law of motion, alternative form of Cauchy's equation, and then we come to the fundamental equation, the most important equation that governs real fluid flow, known as Navier-Stokes Equation, after the name of two famous mathematicians who did a lot of work in the mathematics, physics, and so on, Navier and Stokes. And their work was independent, but this equation is very famous, and in fact it's a nonlinear equation, and in its totality it is still remains unresolved as a full equation. And it is one of the, just for your interest, I like to mention that this is one of the 10 most famous unsolved problems for which, if somebody solves it, I think there is a award of about $1 million or $10 million. I'm not sure about the amount, but there is a prize money that is attached to its full solution. So this equation is solved only by making certain assumption, by reducing it to a soluble condition. Anyway, we do that when we come to it. And its introduction, the Newtonian versus non-Newtonian fluids, a very important consideration and classification of our fluids, because if a fluid does not obey the Newton's law, then different conditions will take place for solution of these equations.